Hi friends, my name is Narasimha and I'm studying my BTech in Institute of Aeronautical Engineering College. Today, as a part of my AAT Tech Talk videos in the subject of data wrangling with Python, I want to explain a topic named, here is a topic name, a survey on large scale machine learning. As we all know, the big data analysis is a formal and essential subject in your day-to-day life. For example, in a common example which in our daily life is Amazon or Instagram, anything, the data which is stored in them is very huge in amount. So if, a role of a data scientist is to store the data of limited and to remove the unwanted data. So it is not possible in manual way, means in a visual manner. So it needs some machine learning techniques. So in this video we will see about that. Introduction. Machine learning endows machines the intelligence to learn patterns from data, eliminating the need for manually discovering and encoding the patterns. Nevertheless, many effective machine learning methods face quadratic time complexities with respect to the number of training instances or model parameters. With the rapidly increasing scale of data in recent years, these machine learning methods become overwhelmed and difficult to serve for real world applications. To exploit the gold mines of big data, large scale machine learning is therefore proposed. So, which I have said before, the machine learning techniques are also not sufficient for handling this kind of data in our day to day life. So, in this situation, large scale machine learning is have been proposed. It aims to address the general machine learning tasks on available computing resources with a particular focus on dealing with large scale data. LML, which is abbreviated as large scale machine learning, can handle the tasks with nearly linear or even lower time complexities while obtaining comparable accuracies. So, which I've said before, the big data should be lengthened shortly, and the needed data should be stored as a role of data scientist. So if it is been done manually, it will take lots of time and it will not result in correct manner of the data. There is no guarantee in it. So these machine learning techniques will do the same work automatically when the data has been inserted, and it will decrease the time complexities and give accurate results. Next, brief analysis of overview of machine learning. First one, reduce the computational complexity based on model simplification. Machine learning models can be optimized based on matrix operations, which generally take cubic computational complexities for square matrices. Besides, most nonlinear methods require extra quadratic complexities for estimating the similarity between pairs of instances to formulate their models. If these models are simplified by being constructed and optimized with smaller or sparser involved matrices, we can reduce their complexity significantly. So these machine learning techniques mainly use the matrix operations, because in matrix operations many forms of data can be stored in a easy manner, in a shortcut way, and the operations can be done easily, and the result can be compared with the practical result, which will give an accurate answer to us. Next, second one, improve the computational efficiency based on optimization approximation. Gradient resistant algorithms cannot always compensate for their huge computations by selecting larger learning rates. Therefore, a more effective manner is splitting data or parameters into multiple subsets and then updating models with these small subsets. As these approximate algorithms can obtain relatively reliable gradients with fewer computations, the reduction in the optimization error can be decreased per computation unit. Third one, enhance the computational capacity based on computation parallelism. During the procedure of model construction and optimization, a high number of computation intensive operations can be performed simultaneously, such as the calculations that are repeated on different mini batches. Built upon parallel processing systems, we can break up these intensive computations and accomplish them on multiple computation devices with a shorter runtime. In this slide, I want to say that actually I said before that huge data can be shortened into small part by using matrix operations. Another way is, if we are, for example, if we have large work to do and we are unable to do because it is so much, we see it. So If we divide the large part of words into subsets, means a small parts, and by doing all the parts of the work and at last combining all that, it will be in easier manner and it will be non-effective manner for us to do the work. In the same way, while a data is getting lengthened shortly, these matrix operations can be used. At the same time, the subsets of the data can be used to reduce the time complexity and space complexity and the mindset of the user. Next, here is a pictorial representation, large scale machine learning. Here I was saying about the model signification, optimization approximation, computer parallelism, hybrid collaboration. In model simplification, there are 4 parts again: kernel models, graph models, deep models, and tree models. And in kernel models, it is used for sampling based approximation and projection based approximation. We are coming to the graph models, label propagation on sparse graphs and optimization with anchored graphs. Welcome to the deep models, filter decomposition and activation reformulation. Welcome to the tree models, relaxation with instance reduction, relaxation with feature simplification. This all model simplification is dependent on computational complexity, reduce the number of required computations for model optimization. Coming to the next one, optimization approximation. In this, there are 3 subparts: mini batch gradient descent, coordinate gradient descent, and numerical integration with MCMC. And here are the some information which are provided by the optimization approximation. Have a look once. Next, computation parallelism. Parallelism is already a small word which is also known to us, that is similarness, sameness. So it is again divided into 2 types: multi-core machines and multi-machine clusters. Multi-core machines are used for adoption of optimization libraries and improvement of input or output operations. Then coming to the multi-machine clusters, it is used for map reduce, graph parallel server, all reduce. So if you have come across graph theory subject, you can have an idea about of graphs, how the vertices and edges are connected to the data which we use day-to-day life, and how the operations are performed by using the matrix operations, and how they are combined to the at last to result to get an accurate results and precision. Next, hybrid collaboration. It has only one part of the gradient. It is divided into compression and delay. Next, model simplification. This whole diagram is again explained in theoretical manner. Model simplification methods improve machine learning efficiency from the perspective of computational complexities to reformulate predictive models and lower computation complexities. Researchers introduce reliable domain knowledge for a small EAP, such as the structures or distributions of instances and the objectives of learning tasks. According to targeted scenarios, the reviewed scalable predictive models consist of 4 categories, including kernel-based, graph-based, deep learning-based, and tree-based, which I have explained before. Advantages and disadvantages of different models. So as we come across all the models in the dive, every model has a pros and cons. So in these models, firstly, kernel and graph-based models can be scaled up and optimized more efficiently than deep models. Besides, experts can introduce their domain knowledge on input features and develop specific similarities for these 2 models. Since the sum of positive semi-definite matrices is still positive semi-definite, it is also easier to merge the similarities of different types of features into a single model. Of note, although graphs generally lead to smaller memory costs than kernels, they are all able to handle the data that is satisfied with the cluster assumption. Secondly, benefit from the hierarchical feature extraction on structural instances. Deep models can obtain much higher classifications accuracies. However, these methods in turn require huge time costs for training the over-parameterized models, although filter recomposition methods reduce the computations remarkably. The architectures demand careful designs. Besides, some deep models are mathematically equivalent to kernelized ridge regressions that learn their own kernels from the data. However, they can only build kernels in finite dimension spaces, and their representations are generally uninterpretable, making predictions hard to be explained. In contrast, tree-based models with hierarchical splitting are more interpretable. Besides, these models can be directly integrated into many other methods for acceleration, such as label trees with binary classifiers. Coming to computation parallelism. Computation parallelism reduces practical times costs from the perspective of computational capabilities. The motivation is mutually independent subtasks can be proposed simultaneously over multiple computing devices. For this purpose, many parallel processing systems can be developed. Distributed processing systems introduce parallelism at two levels, including a number of nodes in cluster and multiple cores within the individual nodes. In this slide, I was saying that computation parallelism is much more better than computational capabilities, because distributed processing systems introduce this parallelism at two levels. That is, first one at number of nodes in a cluster and multiple cores within individual node. Next, these are the examples of distributed processing systems. Once have a look. Here I'm explaining the map reduce, graph parallel, parameter server, all reduce. Which I said before, if you have gone across the graph theory, then you will have idea how to construct this graph and how to analyze this graph. This vertices and edge, vertices says about the data and edges says about the connections between relationship between the data. And by by doing the operations on these graphs, we can get the actual answer and actual required data for our usage, for our further conclusion. At last, our conclusion. Large-scale machine learning, LML, has significantly facilitated the data analysis in a mass scale over the past decades. However, despite these advances, the current LML requires further improvements to handle rapidly increasing data. In this paper, means in this slide, in this lecture, we first surveyed existing LML methods from the independent perspectives, namely model simplification to reduce the computational complexity, optimization approximation to improve computational efficiency, and the computation parallelism to enhance the computational capability. After that, we discussed the limitations of these methods and the possible extensions that can make further improvements. Besides, some important open issues in related areas are present. So, in this whole lecture, I have specified on three parts, that is, model simplification to reduce the computational complexity. Means based on the model simplification, the graph can be constructed and matrix operations can be done on it, and it can be used for further reference, as a further reference. Second one is optimization approximation to improve computation efficiency, means the flexibility and the speed of an work, and the computational parallelism to enhance the computational capability. So thank you, friends. I hope my lecture is useful for you, and thanks for watching.